Today, we're going to discuss about the doping of semiconductor. We use largely two way to make a to dope the silicon. First we use diffusion, and second we can use ion implementation. I'm going to discuss about the dope and diffusion first. This can be rather easy way uh, by applying the dopant material on the surface on the silicon, and we apply heat to make the diffusion. Uh, theoretically, this is theoretically an easier way rather than ion implementation. The dope the diffusion system looks like this. In the chamber, we apply gas and with the heat, and we apply materials in these in those three kinds of phase. Uh, on on which whatever we use, the materials we apply is heated to form gas to and apply to the wafer. This is a simple mathematics with the diffusion. Uh, the flow of the material is determined by the diffusion coefficient and the gradient of concentration. Plus, we use this fixed second law. This is the change of the flow is due to by the input or the output of the material. With the model we use, we can draw the plot from the surface to the lower way with the initial condition n0 with different diffusion coefficients. Uh, after we apply the uh, we can make the uh, we can drive heat to make the diffusion even further, and the graph looks like this from N01 onto N03. The junction because normally the wafers are normally doped with the background dopant, so we can draw plot, and the point is that the dopant we apply and the background dopant. This is the junction. We can heat the wafer, but with thermal lamp and laser, because we need to apply heat as rapid as possible. If not, if we apply heat too much, the junction thickness can be rather too deep, and some material, the crystalline structures can be destroyed. However, in modern semiconductor process, we surely need the shallow junction and the dopant in the source and drain needs to be high, because we need to lower the source drain the series resistance. So we usually use the ion implementation. Before we move on, we have learned about the threshold voltage reduction in the device physics. The deeper the junction with the diffusion region is is even further enlarged and further. Because of the with the further diffusion region, the threshold voltage is lowered to make even further the threshold swing. Next, let's move on to the ion implementation process. This is rather even much more precise rather than the diffusion. However, we normally use the plasma, the ion implementation process is rather expensive. This is the simple structure of ion implementation machineries. We bake the ion and we select the wanted ion and discard the unwanted ion by with the magnetic field. The unwanted because the wanted and unwanted ions are different in their own weight of the ions. So the unwanted ions cannot enter this path. When enter After entering this room, the ion is accelerated by the electrical field and we focus the ion beam to the final wafer to scan to scan the entire wafer evenly. We usually use this plasmic ion beam generator, or we can even use this tungsten filament to tungsten filament. In this tungsten filament, we put electricity inside the filament, and the electron beam is generated to make the ion. When implementing ions, most ions collide with the materials inside and, and stop where normal most of the ions are stopped. However, some ions can be backscattered by colliding other atoms, and even some ions can be channeled deeply through inside. The stopping mechanism of ion is by nuclear stopping and electron stopping. First, when we first apply the ion that is moving fast, first when the ion particle moves inside the silicon, the electrical charge makes the ion move slower, and when the ion is slow enough to make the collision with other nuclears in of the silicon or the police, the collision with the nuclei of atoms can make it scatter and crystal structure can be damaged. When ion velocity is high enough, the stopping is largely due to electronic stopping, and when ion is slow enough, the nuclear stopping is dominating. With those, and moreover, the 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 energy we put to the ion can make the can vary the thickness of the ion punching through, and the and the types of ions can also vary the result. The, Normally, the distribution of the implemented atom forms like the Gaussian mathematical model like this. And because when we make a hard mask to selectively implement, we need to stop the ion inside the oxide, not to get inside to the substrate. We can use some mathematics uh, to decide the thickness of the mask. As I have told you before, the amount of energy we put to the ion can vary the thickness of the ion implementation. So if we use the techniques such as varying the energy and the ion beam with the multiple ion beam implementing, we can make the ion implementation this even this uh, better. As I told you before, some ions can be channeled through deeply inside the atoms. This is because of the crystalline structure of the crystals. By tilting the substrate by tilting substrate, we can make this channel effect less to prevent the channeling. However, if we tilt the device too much, there can be some shadowed areas that the ion beams cannot be reached. Uh, this is why we also apply the ion beam from other angles, but this even makes the ion the ion doping even harder. Uh, because and as I, and because the ion implementation can destroy the crystalline structure of polysilicon, the can, lattice damage can be made, and the semiconductor uh, characteristics can be destroyed. However, this can be cured by applying heat after ion implementation. Uh, by in this pattern or the US semiconductor fabrication technique, there is there are merely 10 dopant ions in one in a single transistor fin. So controlling of doping is even much important than in the past. Thank you for listening.